Here we go. In our continued journey in related rates, we're now going to look at what is known as the shadow problem. Let's check that one out. A 5-foot tall calculus student walks away from a 14-foot tall streetlight at a rate of 3 feet per second. Okay, so right away, I've got a picture that I can draw. So 5-foot tall calculus student would be something like, I don't know, like that. This is not drawn to scale at all. 14 feet, roughly like that, roughly 3 times that height. So that's 5, because the student's height is not changing as the problem goes on, nor is the height of the street light. That would be very strange, right? If either of they're growing as they walk. It'd be crazy. So this is the light source coming off. So the light, like the ray of light coming off the light, and it kind of makes for triangles. And then we have distances that are going to be happening here, because it says how fast is the student's shadow increasing? Well, that would be, and I guess I'll put that in black here. So that would be the shadow right there. And then of course there's the rest of this distance here too. So how fast is the student's shadow increasing? How fast is the tip of the shadow moving with respect to the ground? So there are these two values that are changing in terms of assigning variables before we get rocking with the math. You've got a value of x, and I'll put it anywhere, it doesn't matter, here. And that would be the distance between the student and the light post. Because if this student here we'll draw some legs and some arms, is walking away from the light post, x is changing. Right? So that's a changing amount. And the other amount that's changing is the y value, which we'll just call the length of that shadow from the student all the way out to the ground. And I guess the feet being there doesn't make much sense, because then his feet or her feet are going through the ground. And that's generally not a good thing. So we'll leave it at that. Anyway, so now what do we do with this? Well, the only way to relate a triangle within a triangle is with similar triangles. And you've seen something similar to this in the cone problem. But even before we get into the problem, we've got to separate the triangle. So I've got 14 and then x plus y. This is the distance of the entire large triangle. Then you've got the small triangle that goes on the inside there. There it is. And this is y and a height of 5. Okay, so now from here, what we've got is basically a proportion that we can set up. So you've got 14 to x plus y, 5 to y, and now we can set up a proportion that's going to relate all the variables. Okay, well, a couple different ways we can do this. I'm going to do 14 over 5, right, the corresponding parts, and then x plus y over y. And now I look at that like we do with all our problems from before, and we ask ourselves, can we take a derivative of this and expect a nice value? The answer is we could take a derivative, but we'd need the quotient rule, and there'd be a lot of dx dt's and dy dt's. So why don't we first multiply this out to see if we can neaten this up first before we take a derivative. 14 times y is equal to 5x plus 5y. Okay, so now from here, we subtract 5y from both sides, so that's 9y is equal to 5x. And now, it really doesn't matter technically which variable you solve for, except let's now check out the information we have. From a 14-foot tall streetlight at a rate of 3 feet per second. Okay, so what we've got is that the walking rate would be dx dt is equal to 3 feet per second. That's how fast this is changing, how fast the shadow is changing, how fast it's expanding out from the person. Well, that's different. That would be dy dt. So that means we're solving for dy dt, so I'm going to divide by 9 on both sides. 5/9 x. So now we've got our function. That's actually a really easy function to derive, and this is a perfect problem to again state the importance of getting a function into, or a formula into the form so that taking the derivative is easier. Now we take a derivative with respect to t. So that would be dy dt, or dy dt. 5/9 is just a coefficient. The derivative of x with respect to time t is dz dt. Is that how you'd say it? Dx dt. All right, so then how do we solve for dy dt and what does it represent? Well, that would be how fast the student's shadow is increasing, how fast it's elongating, right? If you walk away from a light source, it would stretch out. So we plug in the numbers we have, 5/9 we have already. Dx dt is the rate at which the student's walking away from the pole. If the student's walking towards the pole, that would be a negative number. And so that would be dy dt, which is the answer to the first question. So we'll simplify that out. 15/9, which simplifies to 5/3. Your units are in a change in y, which would be in feet, per change in time, seconds. Oh, it's beautiful. So 5/3 feet per second. Now, we've got a second question here. It says, how fast is the tip of the shadow moving with respect to the ground? So you've also got the tip of the shadow here, and it's just kind of moving along. two things make the tip of that shadow increase, right? One thing would be how fast the student's walking. That pushes his or her shadow along. The other thing is how fast the shadow's stretching. So you got double action. So the light's standing still. The student is pushing the shadow away from the light, and also the shadow's stretching out too. So we've got to add the rate at which the shadow's lengthening from the student, as well as the speed with which the student is walking away from the light. So for the second question, we would take dx dt, the rate of the student walking, plus the rate of the shadow lengthening. And that is going to give us our answer. So dx dt we're given is 3. dy dt we just solved for. Now we add those together. 3 is the same as 9/3 plus 5/3. And that's equal to 14/3, and our units would still be feet per second. This is one of those classic problems that, again, students have some trouble with, but if we learn to recognize the similar triangles in it, and recognize the importance of solving for one variable to make the differentiation easier, this problem becomes a lot more manageable. All right, I'll see you next time.